Okay, so in this video, let's learn a bit more about the solar system. So, the planets inside the asteroid belt, namely Mercury, Venus, Earth, and Mars, they are called the inner planets. They have a rocky surface, they are solid, and some salient features are that Mercury has no atmosphere because it's too close to the sun, and also it's too small to hold the atmosphere. And Venus is the brightest object in the night sky apart from the sun and the moon. I mean, in the night sky, obviously moon, and it's almost the same size as the Earth, but then its atmosphere has 97% carbon dioxide. So greenhouse effect is extremely high. So it's a very hot planet, and the temperature can reach nearly 500 degrees Celsius. So now you know about how dangerous greenhouse effect is, and Earth's global average temperature is also rising due to increasing percentage of carbon dioxide. Mars is called the red planet because of the soil, which is reddish in color because of a lot of iron oxide in the soil, and it also has a thin atmosphere, mainly carbon dioxide, and it has some ice in the polar caps. And we believe that one of the asteroids from the asteroid belt hit the Earth and caused the extinction of the dinosaurs 65 million years ago. And outer planets are all mostly gas. So Jupiter has a great red spot, which you can see here like an eye. It is a storm which has been raging for centuries, and still it is there. So it's a huge storm. It's bigger than Earth, and it has a moon which has active volcanoes also in it, called Io. And the beautiful rings of Saturn, if you look at them close enough, they're actually made up of rocks and pieces of ice. Then Uranus is tilted 90 degrees, more than 90 degrees. Its axis of rotation is tilted by more than 90 degrees. It also has rings, but which are fainter than Saturn. And then we come to comets, meteors, and meteorites. So comets have very highly elliptical orbits, which bring them very close to the sun, which is called, the closest point is called perihelion, and it also takes it very far from the sun, which is called apogee of the orbit. So while it is coming towards the sun, the solar radiation melts the particles of the comet, and those vapor particles can be seen, which are extending to millions of kilometers long, and they are called the tail of the comet, and they always point away from the sun because the solar wind pushes it. Solar wind is made up of ions and radiation coming from the sun. So sometimes when the meteor manages to reach the Earth without burning completely the atmosphere due to friction, it is called as a meteorite. And this is one example of a meteorite which landed on the Earth, causing the extinction of the dinosaurs 65 million years ago. 65,000 years ago, or here around 50,000 years ago. This crater is 800 meters in diameter. Now you can see the Halley's Comet's orbit, how elliptical it is. It goes beyond Neptune at its furthest region, and it goes closer than Mercury in its nearest approach. So the speed of this comet will change. It will become very slow when it is far away and very high when it is close. It's like when something is if somebody is bungee jumping, as they are falling downwards, their speed increases, and then they start going upwards, and at the highest point, the speed again decreases, like that. So anything which orbits a planet is called a satellite, and the time taken to complete one circle or orbit is called the time period of the orbit. So this is a picture of a satellite in orbit around the Earth, and a geostationary satellite will appear always above the same spot on the Earth. So its time period of orbit should match the time period of rotation of the Earth. So that is the specialty of geostationary orbit, and it will be at some fixed altitude in order to have that time period. So time period of anything which is in orbit, it depends on the distance from the Earth. So further something is, longer the time period. Closer something is to the Earth center, shorter the time period. The actual relation is given by Kepler's law, where it says T square is proportional to R cube, where T is the time period and R is the distance between the planet and the satellite. So we use different types of satellites, like communication satellites, which are in geostationary orbit. Then we have navigation satellites, many of them are used together. So we have a network of satellites, they transmit synchronized time signals. So they are used for the global positioning system GPS. So then you have monitoring satellites like weather satellites, which take pictures of the Earth in different frequencies of light spectrum. Then you have astronomical satellites which are used to explore the space, like the Hubble Space Telescope. Now let's learn a bit more about the sun, stars, galaxies, and the distances between them. So one light year. So the name light year seems like it's a unit of time. The word year seems to make it sound like a unit of time, but actually it's a unit of distance. So one light year is the long distance which light will travel in a time of 1 year. So it's a huge distance. So one light year is around 9.5 into 10 to the power 12 kilometers. A huge distance. You have to multiply the speed of light with 1 year in seconds to get the distance traveled. Now galaxies are a huge collection of stars, and look at this picture. The position of the sun is near the edge of the disk of the Earth's Milky Way galaxy, which is a spiral galaxy. And this picture is this picture of the nearest galaxy to our own galaxy, which is called the Andromeda galaxy. It is 2 million light years away. 2 million light years away. That means light would take 2 million years to travel to that galaxy. And this picture shows you how a star is formed. First you have a cloud of gas and dust, mostly hydrogen, and remnants of stars which would have exploded before that, some supernova remnants. Then due to gravitation, this cloud of gas and dust starts to attract itself, and they start to spiral in a particular direction. And while they are spiraling, they become more and more compact, and at the center it becomes very dense, and soon it becomes hot enough to become a protostar. And once fusion sets in, it becomes a main sequence star, which is like the sun. So whenever the energy is released in a star by fusion of hydrogen gas, it's called a main sequence star. So after that, depending on the initial mass of this cloud, the death of the star will have different types of death. So one way of ending is it will become a red giant star, and then the outer shell will just slowly drift and disappear, and the remnant of the inner core will be a white dwarf star, and the helium will fuse to become carbon in that white dwarf star. After which nothing will happen, it will just gradually cool off. So here this talks about the fusion power in the sun. So at the core of the sun, the temperature is 15 million degrees Celsius, which is very high and sufficient, and the pressure is also high enough for fusion of hydrogen to happen and helium to be produced. Now let's see the different types of deaths of a star. So first is the formation of a red giant star, and the outer shell slowly disappears and leaves behind a white dwarf star. So if the star started out with a little bit more mass than our current sun, then it will become a red supergiant star, and the outer shell will explode. And the explosion is called a supernova, and the remnant star will undergo fusion to become a neutron star. The electrons and protons will fuse together to become neutrons. So suppose the mass was even stronger than this, then instead of a neutron star, it will become the remnant will become a black hole. So it will keep on shrinking, and nothing can escape from it. So in a way, all the matter we see right now around us or in us was at one stage found inside the center of a star or during the energy released during a supernova explosion. So during a supernova explosion, neutrons will be scattered, neutrinos will be scattered. So by observing these particles also, new elements can be found, higher elements can be found. Or they are found in the center of the nucleus by nuclear fusion of smaller elements. So now we come across a new theory called the Big Bang theory, which explains what we see right now. If you observe any galaxy which is further away from us, find that all the galaxies seem to be going away from us. So at first you would think that you are at the center of the universe and everything else is going away from you. But actually if you see every other galaxy also, from their point of view, all the remaining galaxies are moving away from it. So there doesn't seem to be any unique center point in the galaxy, in the universe. So every point is like a center. So you can understand it by analogy with a surface of a balloon which is expanding. So if you have already drawn some pictures of galaxies on the surface of a balloon, as you grow, as you inflate the balloon and it expands, the galaxies will start moving away from each other on the surface of the balloon. And they will also getting bigger. But actually, did the galaxies move? No. Only the surface which was holding the galaxies, it became bigger. So the separation between the galaxies became bigger, but the galaxies were stationary, they were not moving. That is happening with our universe. So we see that the scale factor is increasing. So the distance between the galaxies over time. If you look at any galaxy, the further away it is from us, the faster it seems to be receding from us. And Hubble came up with a law that says that the velocity with which a galaxy is proportional to its distance from us, r, and the proportionality constant is also called Hubble's constant. So using data from multiple galaxies, he calculated the slope of this proportional line, and he got a rough estimate of the Hubble's constant. So now you can use the Hubble's constant to estimate the age of the universe. The Hubble's constant will give you the age of the universe. Now if you ask me how and why, then look at this. So suppose now you are looking at a galaxy which is a distance of d from us, and it is traveling at the speed of v from us. So at one point of time, it was exactly with us or at us or on us, because we were together in a single point. The universe started from a single point. So that is the point where the space-time started getting created. That is the point when time started. So that is the initial time, and now is the final time after the lifetime of the universe. So now the speed is distance upon time. So time is distance upon speed. So distance upon speed, if you do, then you get 1 by h naught. So it turns out to be 13.8 billion years, the lifetime of the universe. And how do we explain the fact that the galaxies seem to be getting away from us faster and faster? How do you explain the fact that the universe seems to be expanding? Whereas we can only think of a gravitational force of the entire matter of the universe, which is going to attract it and try to slow it down. But instead it's accelerating the expansion. So one way is to think of something which is anti-gravity, something which is repelling instead of attracting mass. So we term called dark energy and say that it is causing the expansion between the galaxies and causing the universe to expand at a faster and faster rate. But dark energy and dark matter are all unknown concepts, even though we don't know anything about them. So that completes the chapter of Earth and Space. Now you can practice these questions and then ask me any doubts if you have.